Okay, so welcome to all the speakers of the last session of this Higgs celebration. And we are going to have 3 talks. The first talk would be given by Jenny from DESY on the potential of Higgs physics at ILC. So she obtained her PhD from Aachen in 2000 from the LEP era, but she worked on the searches of Higgs boson at Opal. And later on, she worked on H1 experiment and the measurement of the beam polarization at Hera. And since then, since 2006, she is leading a group at DESY, which is specialized in physics potential, detector performance, and beam polarization measurements for the future e+e- collider, in particular ILC and ILD. And since 2016, she is a member of ILD executive team. And since 2021, she's deputy chair of the physics and the detector working group of the international development team for the ILC. And she's a member of the accelerator working group. And also, she's a coordinator of the physics potential working group of the ICFA, study on physics, experiments, and detectors at e+e- Higgs, Electroweak, and Top Factory. So let's welcome Jenny. So Jenny, I'll give you a notice like at the end of 50 minutes, and we will leave 5 minutes for the discussion. Okay.
That should be fine. And yeah. I'll try to share my slides. Oops. Go to page 1. First of all, would be good. And then share screen. Good. Okay. Let's make this small somehow. Very good.
Yeah, perfect.
Can you see this? Good. Okay. Yeah. Thanks a lot for the kind introduction and for giving me the opportunity to tell you something about. Oops, I shared the wrong slide. I'm sorry. How did this happen? Too many open windows. Okay, what? Now I'm confused. So I think this is anyhow. I think this is actually a bug which remained because I was traveling until an hour ago, and actually in between my usual laptop broke down. So as you see, I'm here, but I had to recover the slides from a previous version. So apologies for the wrong title. So I'll tell you something about Higgs physics at the ILC and a bit more general as well. The main reason why everybody is interested now in electron-positron colliders and especially Higgs factories is that 2 years ago, the European strategy for particle physics made a rather strong statement that an electron-positron Higgs factory is the highest priority next collider. So why did they make this? So why did they come to this conclusion? So, I mean, the actual big questions we have in particle physics are usually closely related to the early history of our universe, which history you can see here from the Big Bang to today. And while you can look back to the late history with astronomy and telescopes, it's really particle physics and accelerators which bring you to the really early times, which are sort of behind the point where the universe became transparent. So the questions we have are things like how can the Higgs boson actually be so light, and what is the mechanism behind the electroweak symmetry breaking? What is dark matter out of? What drives the inflation here in the early phase? And what is why is the universe made out of matter and not antimatter, and what generates neutrino masses, and many others. So all of these questions, the answers can really be found only outside the standard model of particle physics. What we do know is that actually many hints which we have for new phenomena come out of the electroweak sector, including the Higgs, and that's why Higgs physics and its precise study is considered so important. So we know that new particles somehow must be charged under electroweak interactions if they should contribute to this to solving these puzzles. And they're studying the Higgs but also W and Z bosons and their interactions with the top quark of a very high priority. What we do not know so much is the relation actually to the strong interaction. And what we also don't know is the energy scale of new particles. And that makes it very hard to give any guarantee for the direct production of new particles. But nevertheless, I think eventually one will want to explore new energy regimes with a very high proton-proton machine. But, so how do we tackle these big questions at colliders now? Our tools are really the precise study of all the particles we know, plus possibly the discovery, of course, also of new particles. And I mean, assuming that many of you are familiar with the LHC, then of course the most striking difference to the e+e- is that you really collide elementary particles. You can choose different energies of the hard interaction by accelerator operation, and then you basically know the center of mass energy on an event by event level without having to deal with structure functions. Oops, what is happening here? Nothing. So there are several of these proposed Higgs factories on the market. They fall into the classes of circular and linear colliders, and of course the ILC is one of the linear ones, and click the other. So the typical length of the linear colliders to reach 250 GeV is something like 10 to 20 kilometers, depending on the exact technology. And one of the striking features is that it really reaches high luminosities and high power efficiencies at high energies, and that it can deliver spin polarized beams. On the other hand, the circular machines really excel at low center of mass energies at the Z pole and so on. They can have more easily have multiple interaction regions and even have less Beamstrahlung and the like. So this clearly also offers advantages. Both types of colliders foresee long-term visions. For circular colliders, this would be typically the reuse of the tunnel for a proton-proton collider to really explore uncharted territory at the highest energies. And this is actually really one big motivation to drive magnet R&D for high temperature superconducting magnets. For the linear colliders, the long-term vision is different. That's really energy extendability in e+e- either by increasing the length or by replacing accelerating structures with advanced technologies. Let's look at what we produce in e+e- collisions. Here you see the cross-section as a function of the center of mass energy for various interesting processes. And just to orient you, this upper left corner is what we so far explored at LAB, the last high energy +E- collider we had. So now all the proposed projects want to explore this region here up to the top threshold, where circular colliders put a lot of emphasis on going to very large luminosities, thus probing very small cross sections or modifications of cross sections, and linear colliders like the ILC want to go in this direction to higher energies and probe all these processes which pop up here. But let's start here with this corner here, which is sort of the minimum consensus for the Higgs. Before we go there, there are a few other parameters one needs to know about. One, of course, is obviously the luminosity, defining the size of the data set. And just to put this in perspective, the future e+e- colliders aim for a factor of 1,000 to 1,000,000 larger data sets than LAB had. However, the luminosity you get really depends strongly on the invest cost and also on the power consumption which you allow while you operate the machine. So you can always debate how you do a fair comparison here. One should at least be aware that there, of course, also are real life constraints on these things like cost and energy. And then, of course, one always has to ask, whether there are somewhere more fundamental boundaries beyond just the simple statistics, which scales obviously with luminosity, so theory, but and parametric uncertainties, detector resolution, and all that. One other top level parameter, as we say, the third one next to luminosity and energy, would be the beam polarization. And I better explain you this on the next slide, which is dedicated to this, because I'm not even sure whether everybody is really in particle physics and thus really familiar with this. So chirality is very important because the gauge group of the weak and electromagnetic interactions really differentiates between left and right-handed particles, so they are really different. And only the left-handed fermions and right-handed antifermions really take part in the charged weak interactions, so coupled to W bosons. While the right-handed quarks and charged leptons are singlets under this SU2 transformation. So also the couplings to the Z boson are different for left and right-handed fermions. And thus checking whether the differences between left and right-handed particles are as predicted in the standard model is a very sensitive test to new phenomena. Benchmark quantity here is the polarization, which is simply for a bunch of particles defined as the number of right-handed ones minus the number of left-handed ones divided by the total sum. What one can just very briefly, there are 4 classes of effects where this helps. This is can use the polarization to tune out some background processes, especially W pair production or neutrino pair production. You can enhance signals, but most importantly, you can do this thing with the chiral analysis and really probe this difference. And also, it gives you an additional handle for the control of systematics, because the wrong polarization sample usually yields you a signal-free control sample. If you have even 2 beam polarizations, then flipping the positron polarization even controls nuisance effects on observables which rely on the electron polarization. You can read more about this in the literature. If you're interested. So now coming specifically to the ILC and its Strawman running scenario. So the baseline is really to start at the first stage at 250 GeV, the Higgs production threshold. Upgrades foresee to go to 500 GeV or 1 TeV. Further options would be to run at the Z pole and at the WW threshold. And a very important point is that the center of mass energy in ILC is really tunable in a rather flexible way, of course, up to the maximum given by the length and the gradient, but be going lower is usually always possible. The luminosity, the baseline version is just 1.4 times 10 to the 34 per square centimeter and second. And there are 2 possible upgrades, one of them rather cheap, the other one more expensive. And both beams are foreseen to be polarized, the electrons to 80% and the positrons to 30%, which could be upgraded to 60%. So the baseline Strawman run plan could look like this. Starting to explore the Higgs at 250, upgrade the luminosity as soon as you get money for that, take more data, and then upgrade to higher energies. At some point, do a small run at the top threshold to get the top mass very precisely, and so on. So this running scenario is the basis for most of the results I will show in the following. Many of the results are actually based on very detailed simulation of the ILD detector concept. For the other proposed one for ILC, for SID, most of this is rather similar. So just to give you a comparison of what the improvements on the detector are roughly compared to Atlas and CMS, which you might be more familiar with. You see that there are really factors of improvement, I mean, in particular on the momentum resolution, but also in vertexing, jet energy resolution, and also on the hermeticity, so how far you instrument down to the beam pipe. There are the key features of the detector which you need to meet these, or how ILD chooses to do this is to use really as a tracker which introduces very little material, and as the main device, this is based on a time projection chamber, which has the nice feature that it also measures the specific energy loss for identifying kaons and protons, and complements this with silicon. And for reaching the jet energy resolution, the emphasis is really on highly granular calorimeters optimized for particle flow. Those of you who work on CMS might know that parts of the HG-Cal upgrade are an offspring of the technology developed for these detectors. Here in the middle, you see the time projection chamber. So this is, of course, I'm not doing this comparison to tell Atlas or CMS would be bad, but I mean, this is simply a difference in the experimental environment, which enables this much better detector performance, because you have much lower background, much less radiation, much lower collision rate. And so this enables that you actually have a very low material budget, because you don't need to cool and can power pulse your detector instead, switch it off when you don't read it out. And you can also run even trigger without a trigger and record simply everything which comes, which is especially nice if you look for unexpected things. So coming to the minimal Higgs program, I mean, the first thing is, what do we want to achieve actually? And we mentioned in the beginning, we have many questions where the answers lie outside of the standard model. So at the end of the day, the question is, how big could be the effects from physics beyond the standard model on the Higgs properties? So this has been studied a lot in the literature, and you can, depending on which BSM model you look into, you can find rough scaling laws for important parameters. But just to give you a few examples, here from the PMSSM, from a little Higgs model, and for a composite Higgs model. And the important point here is that you see that all the couplings of the Higgs boson to either fermions or bosons of the standard model, they all have different patterns of deviation here from zero, which would be the standard model. So first of all, of course, you would be happy to detect such a deviation, so some point which is away from zero and by a significant amount compared to its uncertainty band. But then once you see these deviations, you can really sort of fingerprint and get very important hints on what actually the new physics could be. You also see that typically all these deviations are at maximum a few percent, which means that you need to get to the percent level with the precision of these measurements if you want to really have any chance to see a deviation. So percent level is the minimum requirement, and the better, the more precise you go, the higher new physics scales you can probe. So why is an e+e- Higgs factory special? So the really big asset is that so that you can measure the total Higgs-Strahlungs cross-section. This works because you know the initial state. So you know the form momentum of the colliding particles event by event. You measure the decay products from the Z, and thus, regardless of what the Higgs does, which decay mode or completely invisible decay or something completely exotic, you will just identify the Higgs by the recoil peak of against the Z. So this you see here for a from a full detector simulation of ILD. And you see that here nicely, you see your Higgs peak above the background. And this is especially if you restrict yourself to simple decay modes of the Z boson, for instance, here in this case to muon, this is completely independent and agnostic to the Higgs decay mode, and thus really gives you the absolute determination of couplings. If you look here at this cross-section plot, you also see why 250 GeV is the place where you want to do this, because there really the whole production is dominated by this Higgs Strahlung, while at higher energies, here this fusion process becomes more important and the Higgs Strahlung's cross-section drops off. But this is the total cross-section, but then you also want to look at all the different decay modes, and I picked a few here which might be interesting. So usually, I mean, different also from LHC, you typically use all the visible decay modes of the Z and nu Higgs, so either Z to neutrinos or the fusion production. So in particular, you also use Z to jets, and thus really all, I mean, the jet energy resolution and jet measurements, but also theoretical modeling of jets play really an important role here. So what I brought here is a bit more detailed study here from ILD in the interim design report, which was published, last year or so, which shows you the expected precision on cross-section times branching ratios for 3 of the hadronic Higgs decay modes, Higgs to BB bar, Higgs to CC bar, and Higgs to blue. This is done here only for one part of the data. So with a final state of nu Higgs and 1.6 inverse autobahn with negative electron polarization at 500 GeV. The 4 colors here correspond to different assumptions on the detector. So the here the lower ones are the sort of current state of the art of the detector performance and actually implemented reconstruction for 2 different sizes of the detector. And you see for this measurement, you don't care much about the size of the detector. That's the first thing. However, for instance, here in the charm, you see that there is a big difference between the sort of realistic analysis and the perfect flavor tag. So for charm, Higgs to charm, there is really a lot of improvement still possible in principle by really becoming more clever and doing a better flavor tag algorithm. On the other hand, for BB bar and glue, there is not much to gain, but you also see if you look at the absolute scale that from this one channel alone, you basically get here the sigma times branching ratio for Higgs to BB bar to the level of 4 per mil. Yeah, I should have done this before. Anyhow, so another input I would like to highlight from these big tables, which exists, which we will certainly not go through, is for instance here the Higgs to invisible constraint. So this is so here you really use the Z to hadron mode and all others, and then look for something invisible on the other side using again this recoil technique. But this time not allowing all decay modes, but really demanding that there is nothing seen in the detector. And this already with the very moderate luminosity, it gives you a quite tight constraint on possible invisible contributions. Of course, for the full data set, this shrinks a lot, as you will see later on. These measurements and many, many more, which we don't have time to go through in detail, are then...
Jenny?
Yeah?
Could you go to the previous slide? Yeah, what is the comment in that blue box you said? For the analogous inputs of the polarization?
Oh, this is... Okay,
yeah.
I was too fast. So this is... So how these things are done is you do the actual Monte Carlo data only for a reduced statistics. So, yeah. And you do them separately for each beam polarization, right? So the results are quoted for the Monte Carlo statistics for which the analysis is actually done. So in this case, this is, for the -80 plus 30, this is actually only 250 inverse femtobarn. And you do the same for the other polarization, right? With different analyses, which are actually differently optimized because you have different backgrounds and all that, right? And then, but then, I mean, these are of course not the final precisions, but these are then sort of combined and scaled to the full running scenario and put into a global fit.
Okay, so this polarization will matter.
Oh, absolutely.
Polarization of the
Wait for the next slide.
Okay,
Wait for
fine.
the next slide. So this is exactly what I wanted to explain you as one of the things which were realized only a few years ago when people really started to do these fits, not in the kappa framework, but in the EFT framework, because nearly then the left-right asymmetry of the cross-section, so measuring with both polarizations separately, gives quite some important input. And this is because in standard model effective field theory, there are actually 3 diagrams contributing to the coupling of the Higgs boson to the Z boson. So in the standard model, you would only have this one. And then in principle, you can also have one with a photon, and you can have this point interaction here, which is actually very toughly constrained by electroweak precision observables. So now what the spin reversal does, if you go from a right-handed electron to a left-handed electron and vice versa, then the standard model diagram flips its sign while the second diagram keeps its sign. So this means that if you measure with both polarization, then you lift the degeneracy between basically these 2 operators describing these 2 diagrams. This you can see in the somewhat old plot, so the absolute values are not quite up to date, but this was the last time this was done in this direct comparison. This is again precision in percent versus the various couplings of the Higgs boson, and here the red is if you combine high luminosity LHC projections with 5 inverse attobarn of unpolarized data at 250, while the green ones are if you combine 2 inverse attobarn of polarized data with high luminosity LHC. And the first thing you see is that for many of those, you are actually below this 1%. But the second thing you see that across the board, the differences between the red and the green are very small, and I mean they are definitely not a factor. What would it be statistically? Square root of 2.5, right? So broadly speaking, this means that for the Higgs physics, 2 inverse attobarn polarized and 5 inverse attobarn unpolarized are roughly equivalent. You can also see this in the latest and greatest, which I bring you here. So from the people who are, the colleagues who are actually doing this new EFT fit of Higgs and electroweak physics for Snowmass, they allowed me to give you a sneak preview on the preliminary results that they produced. And this is this extremely busy plot. We'll take a look at it more closely in a second. But before, I want to highlight what maybe the differences to previous efforts. So one thing they really tried to do this time is to make the inputs from the different colliders as comparable as possible. So they eliminated effects from missing channels from one collider, which has only been analyzed for another collider. So by doing extrapolations, they use a common set of systematic assumptions and common inputs from high luminosity LHC, from low experiment, and so on. The plot I show today has no theory and no parametric uncertainties yet. Of course, this will come in the final version. And the fit also features a really extended treatment of the electroweak sector, which I also cut from the plot because then it would be completely invisible on one slide. And this includes in particular for fermion operators for the experts, which were not, for instance, in the European strategy EFT fit. So let's take a closer look at this. You see this is a log scale, and you have the different couplings of the Higgs bosons. The gray thing is high luminosity LHC projections. And there's an important difference here, namely you only get an absolute coupling out if you assume that there are no exotic Higgs decays. So this means you simply take all the standard model decays, you add them all up, and then you get the total width, and you put as external assumption that there is nothing else. If you alleviate this assumption and allow exotic decays, then you see that from Hadron Collider data alone, you have no constraint on any absolute couplings, right? You could, of course, still constrain ratios of couplings and so on, but not on absolute couplings. So this is the thinner bars. Then you have on the very right-hand side, the muon collider, which I guess we'll probably not talk so much about, but then in the middle, all these rainbow colors, you have the CEPC, the FCCEE, ILC, and CLIC in their various incarnations at various combinations of center of mass energies. One maybe just to have a first digest of this. So these black dashed lines are 0.5%. Yeah, so this is 0.5%, and you see that here across the board, if you look in particular at the free width, so the thin bar scenario, the differences are between the different colliders are small. And for many couplings here, Z, W, gluon, B, and tau, you actually make it to this 0.5% level precision. There are two more interesting ones to gamma gamma and to charm, especially, right, which is very difficult at LHC. You get at least to the percent level eventually. That is so what one can take away here clearly is that there is a huge gain from any of these E+E- machines over high luminosity LHC, which does not mean that high luminosity LHC is bad, but I think it's important if one wants to get such an E+E- collider that one agrees on this point and puts it forward to funding agencies, because if there's no clear gain, then why do it at all? So all E+E- colliders show very comparable performance for the standard Higgs program. Of course, there are differences in the details, but I would say for policymakers, this looks pretty similar. Several couplings reach the few per mil level, and some more are at least at the percent level here, which is good news. So of course, these results are very new, so they are not in what I show you now, but this is of course based on the previous versions. Namely, I want to illustrate how you can use these to actually learn something about beyond the standard model physics. So a couple of years ago, there was an exercise to choose benchmark points from various types of BSM models, and all were chosen such that they would most likely not show any hint for direct new physics at high luminosity LHC. And then what you can do is you can take all your Higgs precision measurements and calculate a chi-squared or whatever, a standard deviation to the standard model, but also between any pair of these BSM models. And this is what is shown in this matrix. So so any field here corresponds to the model discrimination power in standard deviations between the row and the column model. So if you take the first one here, this is how much all these model points would deviate from the standard model. So this was done at the time for high luminosity LHC Higgs precisions plus ILC 250 Higgs and also TGCs in this EFT interpretation. And you see for some you get rather large ones, for others you get at least some signs that there is something going on, and some you would not be clearly able to see clearly. If you add 500 GeV, so this is roughly a factor 2 in precision, yeah, this whole matrix turns green apart from one point, two models which are only separated at 3.9 sigma. Yeah? So this is just an illustration what the power is. I think studies like this need to be.
Previous slide once more.
Sorry?
Previous slide once more, if you can go. What all changed? Previous slide. Okay, fine.
Huh? So probably for the results from the new fit, it would already look much greener already with the 250 and 240 stages of the E+e- colliders already, because the results really improved. Anyhow, so I think this is a nice illustration of how indirect and direct and E+e- and PP can be very complementary in their exploration of new physics. I would add, so far, I did not talk at all about CP properties. So this is, of course, also something which is very important, however, not included in these standard EFT fits. So one important channel for this is Higgs to tau tau. So because the tau decay, of course, gives you a nice handle to measure the tau polarization, and thus you get indication of whether your Higgs was CP even or CP odd. So you can in general assume that that the Higgs you observe is an arbitrary mix of the CP even and CP odd state. And then you have a mixing angle basically between them. And as I said, you explored the tau decay and the tau polarization as polarimeters for this whole gain. And then you can, what you then expect to see is that depending on what this CP angle is, your rate has a different dependency on this phi angle here between basically the tau polarizations. So this is one example where you see how this could be either flat or or follow this curve and this is here the experimental precisions here again evaluated in full simulation of ILD. This then, of course, you can turn into a measurement of the CP angle, and you see that this is, you very nicely get out the input value. So this is a very linear and proportional calibration curve. And turns out that at ILC 250, you would measure the CP phase to better than 4 degrees. Similar things you can also do with the Z-Higgs coupling with different parameters. So for the experts, you see here 5 per mil would be the precision on this admixture here. I would rather want to come to a bit more on what is really specific to linear colliders, namely the Higgs measurements, which are only possible at 500 GeV and above, namely di-Higgs and TTH production. So at the last European strategy, this was here the conclusion, taking all the direct and indirect methods into account. However, the main point I want to stress here is that this figure really only applies for the case that the self-coupling actually has its standard model value. Why is this important? So let's have a look. Let's have a look at the cross sections here. For instance, in proton-proton collisions, here on the right-hand side, you see the cross section for di-Higgs production as a function of the self-coupling in terms of the standard model. So here at 1 is the standard model, right? And then, but then if the self-coupling has a different value, for instance here 2 times the standard model, you really get a quite different cross section, You also see that the individual production modes have different dependency on the self-coupling, which is quite important. So how does this look like in E+, E-? Well, of course, similar, because the basic physics is the same. First of all, here as a function of the center of mass energy for the standard model case, you see that here from 400, 500 onwards, you have the double Higgs Strahlung as a production mode. And at the higher energies, you have di-Higgs production and fusion. They roughly cross at a TeV. So there you have really both processes. And then, of course, at the highest energies for click, you get so high cross-section that you actually can also go to differential distributions, which is very helpful. Again, the relative change of the cross-section, here this is shown here for different center of mass energies and production modes. And you see actually that for Higgs Strahlung type of processes, the cross-section, especially at the lower energies, gets larger when the coupling gets larger, while for the fusion type of processes, the cross-section actually drops and even goes through a minimum here around 1.5 times of the standard model. So here, standard model, and if you go to a 2, like same example as before, you really gain substantial factors here. And red and blue really have orthogonal behavior. So why is this coming about? Well, this is of course because you have many diagrams contributing to di-Higgs production, and only some of them have this triple Higgs vertex here marked with the red dot. So you have interference of all these, and how, depending on the center of mass energy, the mix is different, and you get a different sensitivity, so to say, per cross section on lambda. So the full program is to first of all discover di-Higgs production, and then measure its cross section total, and if you can, differential, and then try to extract lambda. So this is what one has to do, and this is what people try to do and estimate, again in very detailed detector simulations with machine backgrounds and everything. And this is here the result you get as a function of again as a function of the value of the self-coupling. Standard model would be here. And the red line is what you would get at 500 GeV from Higgs Strahlung, and the blue thing is what one would get from the fusion at 1 TeV. And you see that around 1.5, where the cross-section goes through a minimum, you basically lose the sensitivity. But if you combine the red and the blue, then this, especially here in this region of interest for electroweak baryogenesis, this really ensures that you get an at least 10 to 15% precision over really a wide range of lambda. I think I skipped this. This is more, but let's use a few minutes for the top Yukawa coupling. So there, LHC is doing a really good job. I think this this even improved to something like 2% or so. Meanwhile, at 500 GeV and E+E-, you're just at the threshold. You see here in blue the cross section as a function of center of mass energy. So you see 500 GeV is a really stupid energy for this measurement. So of course 500 is a number with 2 zeros in the end, which people chose before the actual mass of the Higgs boson was known. So for more recent proposals, like if you followed Snowmass, the C-cubed linear collider proposed in the US, they directly target 550 GeV, and my personal guess is that when one really gets to an energy upgrade of a 250 GeV machine, one would probably also go to 550 instead. You see there the precision on the top Yukawa coupling, which you get, improves a lot. If you go to 1 TeV, you even get to the 1% level. So this is something to be studied in the future. I think another thing which probably should be revisited is a very interesting study, which was actually done more than 11 years ago by now, actually also, for instance, I think Ruini is one of the authors which did this. That is namely the full CP analysis of the TTH vertex. So for this, you need at least 600 GeV again. So again, reconsider your choice of center of mass energy. And this then gives a few percent sensitivity again to any CP odd admixture in the TTH vertex. And to stress it again, for this measurement, really beam polarization is essential. Otherwise, you don't get enough handle on the CP properties. Maybe a very few minutes actually on the sisters and brothers of the Higgs boson, which it might have. If there are more Higgs bosons, then they must share the coupling to the Z with the 125 GeV Higgs bosons. So this means that any additional Higgs boson basically would have very much reduced couplings to the Z. This we know already now. But of course, what you can do in E+ E- is still to do the same recoil trick as you do for the 125 GeV. So this is now again a recoil mass spectrum for, in green, all the standard model, which includes here, as you see now, the standard model Higgs. And if there would be any other Higgs boson, and one of these additional colorful peaks could pop up. This was, if you do the full study and compare this to a similar study done at lab at Opal, which is here the blue, in terms of the coupling versus mass plane, you see that you gain by 1 to 2 orders of magnitude, even at the 250 GeV machine. You also see in this case, where it was nicely evaluated, that for high masses, you are basically doing perfect with your detector, but at low masses, and the reconstruction of ISR photons gets very important. So this is, again, a region where one could improve the detector and or the reconstruction. Other possible brother and sisters would be, for instance, Higgs xenos, which are actually one of the regions very much preferred by general SUSY fits, as for instance here in this example. And of course, at hadron colliders with high center of mass energy, you can probe very high masses for these beasts. However, the triggerless operation and low and clean conditions allow to probe the very difficult region here of small mass differences. And also this has been studied here for ILC 500, for instance. This is the mass difference between the Chargino and the LSP in GeV. You see here's 1 GeV mass splitting, 100 MeV mass splitting, 10 GeV mass splitting, and the mass of the Chargino. The light thing is the lab limit. So this is the real data limit. These are also real data limits from Atlas, but they are very, they are not a one-to-one comparison because they have much more model dependency and model assumption in it. And ILC 500 would basically, apart from this tiny sliver, cover the whole plane in the same model independent way as the lab limit. Yeah, this brings me to my conclusion. So I hope I showed you that there is a clear and significant physics case in E+ E- collisions for exploring the Higgs at 250 and 350 GeV, and that all E+ E- projects somehow promise a similar performance here. Whether this then should be better combined with ultra precision electroweak at the Z pole, or with further exploration of the Higgs top and BSM physics at 500 GeV and above, is an open point of debate. I personally am convinced that one should not block the possibility of going to high energies in E+, E-, and that the community as a whole would profit from a long-term E+, E- facility somewhere in the world. ILC and CLIC and any linear collider basically offer these features of energy upgradability and long-term perspective, including explicitly advanced accelerator technologies. The exact and or operational energy stages of a linear collider beyond the initial Higgs factory mode can still be defined, taking into account the physics needs and also technological innovations. And there is still really a lot to do also for the physics case and the detector optimization. I list a few examples here. And finally, yeah, you are very much welcome to join the team working on these future Higgs factories, either in general, in the overarching ECFA study, if you don't want to commit to a specific project, or since today I was talking about the ILC, I also put you the ILC contacts down there. Thanks for your attention.
Thanks a lot, Daisy, for finishing your talk just in time. So we have time for a couple of questions. So the talk is open for questions and comments. You could raise your hands. So yes, so Arnab.
Hi, can you hear me?
Yes, Arnab, go ahead.
Okay, thank you. So thank you for the nice talk. I have one question. So as we in ILC, we are targeting for the polarized beams. I hope that will give rise to some systematic uncertainty, because the way we measure the polarization of the beams. So can you please explain a bit, I mean, how this polarization will be measured?
The polarization, yeah, the polarization will be measured sort of instrumentally by two polarimeters before and after the IP to the level of 2.5 per mil. This will be then the time resolved measurements. So the instantaneous ones. The overall scale calibration will be done by, of course, collision data. I don't think I have the exact thing of this with me, but something which is at least relevant. Oh, why is this going so slow here? Yeah, this is the one I wanted. So one typical thing is to do this from W pair production, where you also measure, for instance, triple gauge couplings and many other parameters. And it has been shown in many studies that, yeah, the beam polarizations, yeah, which are here, these two above the red box, and the triple gauge couplings, for instance, yeah, they have basically no correlation. So you get, yeah, you combine this then, of course, with the symmetries, yeah, from difermions and so on, and you typically get to per mil measurement of the polarizations.
Okay, I mean, if just I'm trying to understand the effect of this uncertainty. So because in LHC we have this uncertainty on the luminosity, which has a good effect. I mean, by good in the sense that it has a large effect on the precision measurements. I was just curious about how large it will be when we are going to the precision measurements of the Higgs, let's say.
The luminosity uncertainty.
No, luminosity and also the polarization. So yeah. You so said that it will be of the order of per mil.
The raw measurement, yeah, I mean, this is included in the experimental inputs, for instance, in the fits, right? This is all in there, yeah. So the net effect on the various measurements, of course, depends, yeah. But the only measurement where this really plays a role, decisive role at the end, is if you measure if you measure at the Z pole the left-right asymmetry of fermion antifermion production.
Yeah. Okay.
That is basically the only process where this plays a dominant role. On the contrary, right? I mean, you trade a lot of theory and uncertainties because, as it turns out, the polarized, so the left-right asymmetries often receive smaller, say, much smaller radiative corrections, for instance, than the forward-backward asymmetries and things like that.
Mm-hmm. Mm-hmm. And one more question regarding this: why the polarization for the left-handed and right-handed are not same?
Oh, because it's simply technically much more challenging to produce polarized positrons.
Okay. And one last question. So you mentioned for the ILD the hermeticity is around 5 millirad. What it turns out to be in terms of eta, about how much? 4, 5.
No clue. We don't use eta at all in plus and minus colliders. It's all polar angles.
Yeah, of course, yes.
Have to do the.
I was just trying to understand the coverage because we always talk about eta, and that's why. Okay, thank you.
Okay, so we have hand raised from D406.
Yeah, sorry, mine was a simple clarification. In the page 17, you showed comparison of the different collider. And if I'm not wrong, this muon collider, the precision is very poor. Is it due to the statistics?
What?
Page 17, I think. But compare of this, all this coupling of this Higgs coupling, comparison of the different experiments.
This one. Yeah. So I don't know. I mean, you have to check the Snowmass Electroweak report when it is out. Yeah. But I'm not involved in the muon collider, and I cannot tell you what went in here. Yeah. But my uptake is here that especially you need this run really on the Higgs resonance with here at 125 GeV in order to get an absolute constraint on the coupling, right? So at the 3 TeV and even 10 TeV runs, right, you have a similar problem like at LHC, that you have no constraint on the total cross section here.
Okay, yeah, okay, understood. Thanks.
Okay, are there any more questions? So maybe I have one question for Jenny. So Jenny, what is the future course? I mean, I'm just asking a general question on the future, this ILC or FCC. So how is it going to be envisaged in the near future, at least, in terms of
I think that's unfortunately at the moment unclear for any of these machines, right? I mean, I think I was pretty sure that technically one could do these. I think it's for the circular colliders maybe a bit less clear what it would cost, right? This is simply because they have not been studied so long time. I mean, precisely for the ILC in Japan, I mean, there are now ongoing discussions with MEXT for at least the partial funding of the pre-lab program, which was decided not to be funded last year, right? So this was, yeah, I mean, there has been a list of priority work packages, mainly on the accelerator, which is, there are ongoing discussions between KEK and the Japanese Science Ministry to see what could be funded of this. So it's very hard for a non-Japanese person to judge what the what the actual progress is. Nevertheless, I think one sees also in the Snowmass debate, right, that in the US there is, I would say, reappearing interest in e+e- and especially in various incarnations of linear machines. Yeah, I think as a community, we just need to get our act together, right? Because I think we will not get 2 or 3 of these machines, right? So
of course.
Clearly the next milestone really is probably what Snowmass will and later on P5 will say on this, right? And yeah, what we will hope to hear then next year at some point, I guess, the P5 results. Yeah, and then I mean, especially also as far as Europe and CERN is concerned, right? I think the next European strategy update is considered the one where really CERN has to make up its mind what to do after the high luminosity LHC. Yeah, and probably we have to be patient, yeah, until then at least, before we really know what is going to happen.
Sure.
But
Thanks.
given the, Jenny, I have a small quick question regarding, but given the FCC, the circular machine, if there is a complementary linear machine, that will be really fantastic, combination, right? So what will be the European, what will be the, I mean, what will be the Day5 and then the CERN's standpoint as of now, given the FCC program is being pursued, but the support to the ILC, like, because like yesterday I've been talking to someone, so from the Bell. So
yeah, I mean, that's getting highly speculative, right? I have personally a really hard time to imagine a world where we get 2 of these machines. I think that's really a luxury. If we get there, this would be really a luxury situation. And I think it's pretty clear that, I mean, clearly, yeah, DESY has very tight connections to CERN, and whatever CERN will do, yeah, DESY and Germany will clearly be part of that. However, if really another big machine is built using superconducting RF, I think it's also clear that DESY is even needed for that, right? So, but I really doubt that we will have this luxury problem of having 2 of these machines.
Yes.
But
okay,
maybe
nice answer.
Yeah. Thanks a lot, Jenny, for giving a very nice talk, and you almost made a convincing case for the need of ILC or FCC. So with that, I think we can move to the next presentation. Next talk by my